Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 10, Projective Transformations of Two-Dimensional Forms. Section 95, General Projective Group, Representation by Matrices. The general projective group of transformations in a plane, which, under duality, we take as representative of the two-dimensional primitive forms, consist of all projective collineations, including the identity, and all correlations in the plane. Since the product of two collineations is a collineation, the set of all projective collineations forms a subgroup of the general group. Since, however, the product of two correlations is a collineation, there exists no subgroup consisting entirely of correlations. Footnote: a polarity and the identity form a group, but this forms no exception to the statement just made, since the identity must be regarded as a collineation. According to the point of view developed in the last chapter, the projective geometry of a plane is concerned with theorems which state properties invariant under the general projective group in the plane. In particular, the principle of duality may be regarded as a consequence of the presence of correlations in this group. Analytically, collineations and correlations may be regarded as aspects of the theory of matrices. The collineation x sub I prime equal summation j equal 1 to 3 a sub ij x sub j I equal 1 2 3 may be conveniently represented by the matrix A of the coefficients a sub ij. A equals the matrix A sub ij equal the matrix by column A11, A21, A31, A12, A22, A32, A13, A23, A33. The product of two collineations A equal matrices A sub ij and B equal matrix B sub ij is then given by the product of their matrices. BA equals matrix B sub ij times matrix A sub ij equals B11, B21, B31, B12, B22, B32, B13, B23, B33 times the matrix A11, A21, A31, A12, A22, A32, A13, A23, A33 equals the matrix B11, A11 plus B12, A21 plus B13, A31, B21, A11 plus B22, A21 plus B23, A31, B31, A11 plus B32, A21 plus B33, A31, B11, A12 plus B12, A22 plus B13, A32, B21, A12 plus B22, A22 plus B23, A32, B31, A12 plus B32, A22 plus B33, A32, B11, A13 plus B12, A23 plus B13, A33, B21, A13 plus B22, A23 plus B23, A33, B31, A13 plus B32, A23 plus B33, A33. The element of the ith row and the jth column of the matrix BA being obtained by multiplying each element of the ith row of B by the corresponding element of the jth column of A and adding the products thus obtained. It is clear that two collineations are not in general commutative. Of the two matrices, A11, A21, A31, A12, A22, A32, A13, A23, A33, and A11, A12, A13, A21, A22, A23, A31, A32, A33, either of which is obtained from the other by interchanging rows and columns. One is called the conjugate or transposed matrix of the other. The matrix A11, A12, A13 A21, A22, A23, A31, A32, A33 is called the adjoint matrix of the matrix A. The adjoint matrix is clearly obtained by replacing each element of the transposed matrix by its cofactor. Equations 2 of section 67 show that the adjoint of a given matrix represents the inverse of the collineation represented by the given matrix. Indeed, by direct multiplication, the matrix A11, A21, A31, A12, A22, A32, A13, A23, A33 times the matrix A11, A12, A13, A21, A22, A23, A31, A32, A33 equals the matrix A0, 0, 0, A, 0, 0, 0, A. And the matrix just obtained clearly represents the identical collineation. Since when a matrix is thought of as representing a collineation, we may evidently remove any common factors from all the elements of the matrix. The latter matrix is equivalent to the so-called identical matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. Footnote: in the general theory of matrices, these two matrices are not, however, regarded as the same. It is only the interpretation of them as collineations which renders them equivalent. Furthermore, equations 3, section 67, show that if a given matrix represents a collineation in point coordinates, the conjugate of the adjoint matrix represents the same collineation in line coordinates. Also, from the representation of the product of two matrices just derived follows the important result: the determinant of the product of two matrices, collineations, is equal to the product of the determinants of the two matrices, collineations. From what has just been said, it is clear that a matrix does not completely define a collineation unless the nature of the coordinates is specified. If it is desired to exhibit the coordinates in the notation, we may write the collineation x sub I prime equal summation a sub ij x sub j in the symbolic form x prime equal the matrix a sub ij times x. The matrix A sub ij may then be regarded as an operator transforming the coordinates x equal x1, x2, x3 into the coordinates x prime equal x1 prime, x2 prime, x3 prime. If we place A bar sub ij equal to A sub ji, the matrix conjugate to the matrix A sub ij is the matrix A bar sub ij. Also, by placing A bar sub ij equal to A sub ji, the adjoint matrix of the matrix A sub ij is the matrix A bar sub ij. The inverse of the above collineation is then written x equal the matrix A bar sub ij times x prime. Furthermore, the collineation x prime equal to the matrix A sub ij times x is represented in line coordinates by the equation u prime equal the matrix A sub ij times u. This more complete notation will not be found necessary in general in the analytic treatment of collineations when no correlations are present, but it is essential in the representation of correlations by means of matrices. The correlation 1 of section 94 may clearly be represented symbolically by the equation u prime equal the matrix A sub ij times x, where the matrix A sub ij is to be regarded as an operator transforming the point x into the line u prime. This correlation is then expressed as a transformation of lines into points by x prime equal the matrix A sub ij times u. The product of two correlations u prime equal the matrix A sub ij times x and u prime equal the matrix B sub ij times x is therefore represented by x prime equal the matrix B sub ij times the matrix A sub ij times x, chiefly equations 4 of section 94, or by u prime equal matrix B sub ij times matrix A sub ij times u. Also, the inverse of the correlation U prime equal the matrix A sub ij times X is given by X equal the matrix A bar sub ij times U prime, or by U equal the matrix A bar sub ij times X prime. Exercise. Show that if the class pi is the set of all collineations in a plane and gamma sub 1 is any correlation, the set of all correlations in the plane is the class pi gamma 1, so that the two sets of transformations, square brackets pi and square brackets pi gamma sub 1, comprise the general projective group in the plane. By virtue of this fact, the subgroup of all projective collineations is said to be of index 2 in the general projective group. Footnote: the subgroup square brackets pi of a group is said to be of index n if there exist n-1 transformations gamma sub I equal 1 to ... n-1, such that the n-1 sets square brackets pi gamma sub I of transformations together with the set square bracket pi contain all the transformations of the group, while no two transformations within the same set or from any two sets are identical.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.